All right. How's everybody doing today? Cool. Okay. Hopefully everybody enjoyed the field trip on Thursday. I think it was pretty cool. The tour guide seemed to be pretty good, so yep. All right. Today we're going to start with a quick review of series circuits and parallel circuits. We've talked about both of these in the past, so we'll just do a brief review of those. And then we'll go on to the main topic for today, which is series parallel. So just like the name implies, a series parallel circuit has some elements in series and some elements in parallel. And this is the vast majority of circuits in the real world. So we'll talk about that a little bit more. We'll talk about why we care, and then how we analyze these circuits. And fortunately, there's not really a whole lot of new information about or new techniques for analyzing series parallel circuits. Really, all we're doing is we're taking what we already know about series circuits and parallel circuits and just applying that over and over again. So we're not really learning, you're not going to have to learn a lot of new stuff. You're just going to have to reuse what you already know. Okay? So we'll talk about how we can find the equivalent resistance in series parallel circuits, and then we'll do some examples on the board. Then we'll move on to our lab preview. So in today's lab, we'll do some multisim, a circuit on a breadboard, and we'll also use a lamp board. So this is just what it sounds like. It's a board that has some lamps on it, and you'll get to see those light up, and I'll show you how to connect wires to those. For homework, I'd like you to work on the crossword on page 71. Now, I think that on the syllabus and reading list, this was assigned earlier, but I'm not sure that I actually put it up on the board. So some of you have already done this, and that's awesome. If you have done it already, then that's just one less thing to worry about. If you have not done it yet, then please work on that, okay? So any questions before we get started? All right, so then let's start with a quick review of series circuits and parallel circuits. So we said that for a series circuit, that was something like this. We had resistors connected end to end with nothing in between. And say you had a 1 kilo ohm resistor here and a 4 kilo ohm resistor here. If you wanted to find the equivalent resistance, that is just the sum of those two individual resistances, so that would be 5 kilo ohms. Okay? And in series, we said that is the current the same or different for all of the elements? Same. The same. So the current is the same. Bless you. Because remember, current is how much electricity is flowing through the circuit, and in a series circuit, the end of one component is connected to the beginning of the next. So any current that flows out of the first element has to flow directly into the second. So the current is the same, but what about the voltage? Is that always the same, or can that be different? Yeah, so the voltage may be different. Now, so that's for our series circuits. We also talked about parallel circuits. We said that a parallel circuit is a circuit where the beginning and the end of every component, or the beginning of every component is connected to the beginning of every other one, and the end of every component is connected to the end of every other one. So if, say, this was 5 kilo ohms there and 20 kilo ohms there, then if we wanted to find the equivalent resistance, we would use that formula. R total is 1 over R1 plus 1 over R2. And then you could continue that for every resistor that you had. So the equivalent resistance here would be, if you did that formula, you would find that it's 4 kilo ohms. So is the equivalent resistance in a parallel circuit greater than individual resistors or less than individual resistors? Less. It's always less. The total resistance is always less than the smallest resistor in the parallel circuit, because when you're putting resistors in parallel, you're giving the electricity more paths that it can take. And so it's easier for it to flow. So that's how we find the equivalent resistance. And in parallel, is the voltage the same or different for each of the components?
Same.
It's the same. That's right. Because the beginning of one component is connected to the beginning of every other component, so the voltage at the beginning of every component is the same, and likewise at the end, all of the voltages are the same. So the difference across every component is the same. So in a parallel circuit, the voltage is always the same, but what about the current? Is the current the same? No. Current may be different. So hopefully all of this looks pretty familiar. We talked about this before. Honestly, hopefully, I'm hoping that you're all pretty bored seeing this already, because that means that I've kind of drilled it over and over again, and that's what we want, because this is the type of stuff that we're really going to be focusing on. This is kind of the foundation, and this is the information that we're going to use to analyze series parallel circuits. Okay? So are there any questions about series circuits or parallel circuits before we go on? Okay, cool. All right, so then let's go on to our main topic for today, which is series parallel circuits. So series parallel, a series parallel circuit just means that some components are in series and some are in parallel. So some examples might be something like this. You could have a resistor there and then one there and one there. So you can see that these two resistors are in parallel, but then this part of the circuit is in series with this resistor over here. So that would be one example of a series parallel circuit. Another example might be something like this. So these two resistors are in series because the end of one is connected to the beginning of the next. But then this left-hand branch of the circuit is in parallel with the right-hand branch. So anytime you have some elements in series and some in parallel, that is a series parallel circuit. So that's what they are. So why do we care about these? Well, really, almost any circuit in the real world is a series parallel circuit. They almost all contain some elements in series and some in parallel. So if you want to analyze other people's circuits or design your own, you're going to want to understand how series parallel circuits work. Okay? So that's why they're important. So how do we analyze these circuits? Well, basically, the first thing that we did when we analyzed series circuits was that we found the equivalent resistance, right? First thing we did when we analyzed parallel circuits is we found the equivalent resistance. So same thing goes here. The first thing we usually do when we're analyzing series parallel circuits is that we find the equivalent resistance. So in order to do that, like I mentioned at the beginning of class, you're not really going to need to learn a lot of new techniques. You're just going to apply what you already know. And the only difference is that you might have to apply that several times. So let me show you what I mean. Okay? So let's say that we have a circuit that looks like this. We've got a 20-volt power supply. And then we've got a 1 kilo ohm resistor here, a 3 kilo ohm resistor here, and then over here we have a 4 kilo ohm resistor. So is this circuit a series circuit, a parallel circuit, or series parallel?
Series parallel.
That's right. And how do you know? That's right. That's right. Some are in series and some are in parallel. So these two resistors here are in series because the end of one is connected to the beginning of the next. And this branch on the left is in parallel with this branch on the right. It's kind of like this up there, right? So it's a series parallel circuit. So if we're finding the equivalent resistance, we can't just use the series formula or the parallel formula. But what we can do is we can use those formulas to find the equivalent resistance of certain parts of the circuit. Okay? So that's what we're going to do. So the first thing is we look at this circuit and we try to find any elements that are in series or in parallel. So do you see any resistors that are in series or in parallel?
Yep.
Yes.
Yeah. What do we have?
3 and 1 kilo ohm are in series.
That's right. That's exactly right. The 1 kilo ohm and the 3 kilo ohm are in series. So what we can do is that we can use our series resistance formula to find the equivalent resistance for that branch of the circuit. And then we can redraw the circuit using that equivalent resistance. So we still have our 20-volt power supply over here. But now we want to combine the 1 kilo ohm resistor and the 3 kilo ohm resistor into their equivalent resistance for series. So what formula do we use when we're finding the equivalent resistance for series? Yeah, we just add them up, exactly. So 1 kilo ohm plus 3 kilo ohm, that gives us 4 kilo ohms. Perfect. So that branch of the circuit has a 4 kilo ohm resistance. And now this other branch over here stays the same for now. So that one also has a 4 kilo ohm resistance. So this circuit is now equivalent to our original one. Okay? So Is everybody with me so far?
Yeah.
Okay. All right, cool. So, so now what we do is we just apply that process again. We look for any resistors that are in series or in parallel, and then we use our knowledge of those circuits to find the equivalent resistance. So do you see any resistors in series or parallel here? Yeah, the two resistors are in parallel because their tops are connected to each other and the bottoms are connected to each other. So we can use our parallel resistance formula to find the equivalent resistance for this circuit. So what we do is we still have our 20-volt power supply, but now we want to find the equivalent resistance of these two resistors in parallel. Now, those two are the same value. So do we have to use that long formula, or can we use a shortcut?
Short formula.
That's right, we can use a shortcut. And what is that shortcut?
Take the resistance divided by the number of resistors.
Yeah, exactly. So, right, so we take the value of one resistor and we divide it by the number of resistors. So we have one resistor is 4 kilo ohms. We got two of those, so the equivalent there is 2 kilo ohms. And now, when we get down to just one resistor value for the entire circuit, that's our equivalent resistance. So for this circuit, we could say that the equivalent resistance is 2 kilo ohms. So we could call this R1, R2, and R3 here, and say we wanted to find the kind of everything we wanted to know about this circuit. So we could say that we wanted to find the total voltage, the total resistance, and then the total current, and then the voltage for R1, R2, and R3. And then also the current for R1, R2, and R3. So we know what the total resistance is. We just calculated that. That's the 2 kilo ohms. So our equivalent resistance for the entire circuit is 2 kilo ohms. What about the total voltage? Do we have to do calculations to find that? No, exactly. That's just the voltage that comes from the power supply. So that's 20 volts. And how could we find the total current for this circuit?
Voltage over resistance.
That's exactly right. We can use Ohm's law because we know the total voltage and we know the total current, or the total resistance. So we can use Ohm's law to find the total current. So remember, Ohm's law is like this. We've got V, I, and R. So if we want to find the current, we write down I equals, we cover that up and see that it's V over R. So that would be 20 volts over 2 kilo ohms. Now, can I just say divide 20 volts by 2 and get a total of 10 amps for this whole circuit?
No.
No, exactly. And why not? Yeah,
Well, yeah, because of the engineering notation, the kilo ohms.
right, exactly. This isn't just 2 ohms, this is 2 kilo ohms. That's exactly right. So before I do my calculations, I always make sure that everything is in raw units. There's no prefixes, no kilo, or mega, or milli, or anything like that. I convert everything to raw units first, and then I do my calculations. That way the answers come out in raw units. So this becomes 20 volts over 2,000 ohms. So what's 20 over 2,000? Anybody have a calculator?
0.01.
Yeah, 0.01 amps. And remember, the unit is just the raw unit for that whatever that is. So in this case, it's just amps. It's not milliamps, it's not kiloamps, it's nothing else. It's just amps. So this is 0.01 amps. Now, once I have that, I can convert that into, and use my engineering notation to, if I want. So if I wanted to convert this to milliamps, what would that be?
10.
Yeah, I would multiply that by 1,000 or move the decimal point 3 places to the left, or to the right, I'm sorry, and that would give me 10 milliamps. So that's the total current for this circuit. So does anybody have any questions about how we found that? All right, so we can say that the total current here is 10 milliamps. And we can write that in over here too, 10 milliamps. And since these circuits are all equivalent, if I know the total current for this circuit, that's going to be the total current for this circuit over here as well. 10 milliamps. Okay? Yeah?
I just wanted to ask, why are we converting it to milliamps again?
You can, or you don't have to. It's, I like it because I don't have to write any decimals that way. But oftentimes it's up to you. The engineering notation can save you having to write a lot of zeros if there's a lot of zeros there. Sometimes a quiz or homework will ask you to enter your value using particular units. So it might ask for the answer in milliamps, or it might ask for it in amps or something like that. But if it's not specified, then it's kind of your preference.
Thank you.
Yeah. Yeah, other questions? Okay. All right, so that's the total current here. Now, the kind of one of the hardest parts about series parallel circuits is trying to look at the circuit and decide what to work on next. So we still want to find the voltages and currents for all of these resistors, but it's kind of, sometimes it can be a little challenging to decide which one to tackle next using the information that you have. And it's different for every circuit. There's not one size fits all procedure that will work for every circuit. You just kind of have to look at the circuit and see what information you have, and then try to use that to figure out, what to work on next. So, anybody want to hazard a guess about what we could work on next?
Let's start with the series since it's first in line.
Yeah, that would be. It is kind of to the left of the circuit, so that would be good. Unfortunately, basically for Ohm's law, you need to know two of these three things for a particular resistor, and we don't. So we have the resistance values for both of these, but we don't know the specific current or the specific voltage for either one of those right now. So I don't think that we can work on those yet. Yeah.
Well, couldn't you could do the voltage of R1 and R2 because of how they're parallel, R1 and R2?
So
You can find R1, yeah.
right. So yeah. So they're in they are in series. So their voltages could be different from each other, but their current will be the same. So I would look at R3 first because we know. Can we figure out the voltage across R3? Yeah, because R3 is connected with these wires to the power supply, and so there's 20 volts across the power supply, so there must also be 20 volts across R3. Does that make sense?
Oh,
Yeah, remember, because we could call this point ground, and that would be 0 volts. So then there would be 0 volts there and 0 volts there. And similarly, you would have 20 volts there and there and there. So we've got, so we can use that and write down the voltage for R3. So that's 20 volts. And then now we know the voltage and the resistance there. So can we figure out the current? Yeah. And what law do we use for that? Ohm's law, exactly. So that's what we do. We want to figure out the current here again. So we use this formula. We've got V over R. So that the voltage here is 20 volts, and then the resistance is 4 kilo ohms. So do I just do 20 over 4 and I end up with 5 amps? No. I have to convert that 4 kilo ohms into raw units. So that's 20 volts over 4,000 ohms. So what does that come out to be? Anybody have a calculator? What's that?
It's 5 milliamps.
Yeah, perfect. So 0.005 amps.
Or amps, yeah.
Yeah, if you did that on the calculator, which is 5 milliamps. So that's the current that's flowing through R3. And I can write that down for my current here for R3. Perfect. So how much current is flowing through this wire in the circuit? Yeah, 5 milliamps, exactly. Because that all flows down through R3. So that's perfect. So now we can look at our circuit and we can say that we've got 10 milliamps flowing in to this little junction right here. We've got 10 milliamps flowing in there. 5 of it is flowing out to the right. So the rest of it has to be going down this way. So how much is going down that way? 5 milliamps, exactly. And how much is flowing through R2? 5 milliamps, exactly, perfect, because they're in series. All right, excellent. So now we can write down the current for R1 and R2. So 5 milliamps for both of those. So in this case, it turned out that the current was the same for all of the elements. That's not always true, but in this case, it was. Now we know the current for R1 and we know the resistance, so can we find the voltage? Yeah. So we'll use Ohm's law for that again. So we'll write down V, I, and R. That's Ohm's law. If we want to write down the voltage, we write down V equals, we cover that up. We see that it's I times R. And so in this case, I for R1 is 5 milliamps. And then the resistance there is 1 kilo ohm. So again, I want to convert all of these to raw units before I do the multiplication. So that 5 milliamps is 0.005 amps, and then 1 kilo ohm is 1,000 ohms. So when I multiply these two together, that gives me 5 volts. So I have 5 volts across R1 there. So I could do the same thing for R2 and use Ohm's law with 5 milliamps and 3 kilo ohms, and I could calculate the voltage that way. But I could also use kind of another kind of trick here, which is that I know that there's a 20 volt difference from that point down to there. And of that 20 volts, 5 of it is across this resistor. So the rest must be across this resistor. So what does that leave? What voltage do we have across this resistor? 15, exactly. So that's another way to find that voltage. So in electronics, there are often multiple ways to find the right answer. It's helpful often to know several different ways so you can kind of choose whichever one is easiest and works best in a given situation. So the voltage across R1 is 5 volts, and across R2 is 15 volts. So that's how we figure out everything about that circuit. So are there questions about that? Yeah.
When we're approaching these problems, do you have any tips on what's the best next thing to do? Because that's my problem. I try to figure out
Right.
what to do next.
Right. Well, basically, the first thing I would do is find the equivalent resistance, and then from that you can find the total current, and then after that you just have to look and see what information you have and try to find one component where you have, 2 out of the 3 pieces of Ohm's law. So in this case, we used R3 because we knew the voltage and the resistance there. So we started with that. And yeah, you just basically have to kind of work from there and build up your knowledge, and then, yeah, kind of look and see what other components you might have where you know 2 out of these 3 things. Yeah. Yeah.
In this scenario, what could, on that circuit, what could have changed to make the amps not all the same? And what is it? Is there any quicker method of just eyeballing it and being like, okay, so I kind of think that the amps aren't going to be the same for this one?
Well, sure. So that's a great question. So basically, why was the current the same in both of these branches? And is there a way to kind of look at this and tell right off the bat that might be the case? Well, when we found the equivalent resistance for those 2 branches, we found that both of those branches had an equivalent resistance of 4 kilo ohms. And that's really why the current was the same in both of them. So if you saw that each branch has an equivalent resistance and they're in parallel, then that's when they would have the same currents. And if the resistances had been different, that would be an indication that the currents would be different. Yeah.
And would there be any change if instead of, like, say, R3 was there, it was on the top?
Yes, and I'm glad you asked, because we're going to look at another circuit that's very much like that right now. And in fact, the circuit I'm about to show you is the circuit that you will be building and measuring and analyzing on the midterm. Okay? So I know that often wakes people up a little bit. So yeah, so are there any other questions about this before we move on? We'll do one more example. All right. All right. So, the midterm circuit is going to be in this shape. So we'll have a power supply over here. We'll have a resistor there, resistor there, resistor there. So now we've got one on the top, like you were asking. And then we'll also have a resistor over here. So this is the shape of the circuit that you will build. Now everybody's midterm will have different values for the resistors, and the power supply value in this example is 36 volts. In your midterm, I think it's going to be 12. So you will have different numbers in your midterm, but this is the shape of the circuit that you're going to build. So, so this will be kind of the first look that we'll have at it in this class. We'll talk more about this when we get closer to the midterm, and we'll review it again. But we'll actually be building this circuit in our lab today also. So I figured that this would be a good chance to take a look at it and kind of figure out how to analyze it mathematically. And then in the lab, you'll actually get to work with it and build it and see how you can make the measurements. Okay? So,
Two parallel circuits?
no, not exactly. So we'll see that in just a minute. So up here, we'll have a 4 kilo ohm resistor. Down here, 6 kilo ohms. Over here, 6 kilo ohms. And then 3 kilo ohms. So we'll call this R1, R2, R3, and R4. So just like before, we want to find the total voltage and the total resistance, the total current, and then the voltages for all of the resistors, and then also the currents for all of the resistors. Okay, so just like before, the first thing that we want to do is find the equivalent resistance for this circuit. So, and remember what we said is we look for any resistors that are in series or in parallel for the circuit. So do you see any resistors that are in series or in parallel? Yeah, so what do we have? Yeah, Stephanie.
You got R3 and R4 are parallel, so you can find the equivalent of that.
Perfect.
And simplify it.
Yeah, exactly. So, so that's a perfect place to start. So we got 36 volts here, and then we'll keep the other resistors the same. So this will still be 4 kilo ohms, and then down here we'll still have 6 kilo ohms. But now we want to find the equivalent resistance for these two. So can we just take one of their values and divide by 2 resistors? No, because they're different values. That formula would only work if they were the same. So we have to use that equivalent resistance formula. So we could say that R3 in parallel with R4, these two little vertical lines means in parallel. So R3 in parallel with R4 is, we'll call that resistance R34, and we'll say that that's 1 over 1 over R3 plus 1 over R4. So so this is 1 over 6,000 plus 1 over 3,000. So does somebody have a calculator? What does that come out to be? Yeah, perfect, 2,000. So this is 0.001 or 0.166, something like that. Anyway, yeah, so the equivalent resistance comes out to be R34 equals 2,000 ohms. So we can redraw those two resistors as just one equivalent resistance of 2,000 ohms, or 2 kilo ohms. So any questions about how we got that?
It's just zero.
Yeah, exactly. So now we see if we can find any resistors that are in series or parallel. So are these resistors in series or parallel? They're all in series, exactly. Even though they're not in a straight line, remember the important thing is that the end of one resistor is connected to the beginning of the next, and the end of the second one is connected to the beginning of the third. So these are all in series. They have nothing in between them. So these are all in series. So we can find their equivalent resistance. And how do we find that? Add them up, exactly. So 4 plus 2 plus 6 gives us 12 kilo ohms. So we can say that this is an equivalent resistance of 12 kilo ohms. So that's our total resistance, 12 kilo ohms. And what's our total voltage here? 36 volts, perfect. Just the voltage from the power supply. All right. And now, what can we find next from here?
Total current.
That's right, the total current, because we know the total resistance and the total voltage. So we use Ohm's law. We say I equals V over R. So that is 36 volts over 12,000 ohms. So that comes out to be, anybody have a calculator? What is that?
3 milliamps.
Perfect. So 0.003 amps, which is 3 milliamps. So that's our total current. So remember, the total current is the current that's flowing out of the power supply. So that's 3 milliamps. And since these circuits are all equivalent, that means that we have 3 milliamps flowing out of this power supply as well. And how much is flowing back into the power supply, by the way? 3 milliamps, exactly. The current flowing out is always the same as the current flowing back in. So, yeah, so we have 3 milliamps flowing back in there, and also 3 milliamps flowing back around there. Yeah. Okay. So now we come to the hard part again. We have to figure out what to work on next. So anybody have any ideas about what we could look at next? R4. Okay. I wouldn't start at R4 because we don't have the voltage or the current for that one yet. So do we have voltage or current for any of the other resistors? R1. Yeah. And do we know the voltage or the current for R1? Yeah, the current, because the current that's flowing out of the power supply has to flow directly into R1. It has no other place that it can go. So all of that current has to flow right into R1. So how much current is flowing into R1? 3 milliamps, exactly. Do we know the current for any of the other resistors yet? Yeah.
The resistance across R2 is also 3 milliamps.
That's right. The current through R2 is also 3 milliamps because we know that the current flowing out and going back into the power supply is 3 milliamps, and the only place that can come from is R2. So all of that current has to be coming through R2. So the current for R2 is also 3 milliamps. All right. Everybody with me so far? Yeah? Okay. All right, so we got the 3 milliamps for both of those, and now, so we can draw those in. So we have 3 milliamps there, and 3 milliamps flowing down there. So what could we work on next? Yeah.
We could either do resistor 1 or resistor 2, since we know that we can find their voltage, because we know the current and resistance.
Exactly, exactly. So we can use Ohm's law with R1 or R2. So let's just start with R1, since that's on top. So, so again, we use Ohm's law. So it's like that. We want to find the voltage, so we write down V equals, we cover that up. We see that it's I times R. So V1 is I1 times R1. So that, in this case, I1 is 3 milliamps, or 0.003 amps. And then R1 is 4 kiloohms, so 4,000 ohms. So that gives us a total of 12 volts. So the voltage across R1 is 12 volts, and we can draw that in here. And we can do the same sort of thing for R2. So we can say V2 is I2 times R2. So that is, so I2 is still 3 milliamps, so 0.003 amps. And then R2 is still 6,000 ohms. So 3 milliamps times 6,000 ohms gives us a total voltage of 18 volts. So the voltage across here is 18 volts. So now there's a couple ways that we can go. So we figured out everything about R1 and R2. We just need to find the information about R3 and R4. So so one way that we can look at it is we can look at this intermediate circuit here. So we know that there's 3 milliamps flowing that way. So then how much of that current is going to be flowing through this resistor here, R3, 4?
3 milliamps.
Exactly, 3 milliamps. So we know that current, and we know that together those have an equivalent resistance of 2,000 ohms. So we can use that to find the voltage across those. So we would say that the voltage for R34 is I34 times R34. So in that case, that would be 0.003 amps times 2,000 ohms. So that gives us 6 volts. So we can say that there's 6 volts across those points in the circuit. So that means that there is 6 volts there, and also, well, yeah, 6 volts there. Basically, yeah, 6 volt difference between here and there.
We couldn't have subtracted 12 plus 18 from the 36 like we normally do.
Well, yeah, so that's the other way to do it. Yeah, so you could see that we have 36 volts total. So you would have to have kind of 36 volts for between these 2 points, and so what you could say is that this point is ground, or 0 volts. This point would go up by 36 volts, so we have 36 volts there. And then we're going down by 12. So we're starting at 36, going down by 12. So what voltage does that leave at that point? It's 24 volts, right? And then over here, we're starting at 0 volts. We're going up by 18, so we would have 18 volts at that point. So the difference between these 2 points would be 6 volts. So that's another way to do it. Again, in electronics, there are often multiple ways of getting the right answer. So these are 2 different ways of looking at it that both give you the right answer. So questions about that? All right, so the voltage across R3 is 6 volts, and also across R4 is 6 volts. So now all that's left is to use Ohm's law to find the currents. So we can say that I, R3 is, we cover that up and we see that it's V over R. So V R3 over R3. So that would be, the voltage is 6 volts. And then the resistance is 6,000 ohms. So 6 volts over 6,000 ohms gives you 0.001 amps, which is 1 milliamp. So that's 1 milliamp. And again, so we have 1 milliamp flowing through R3 there. So again, we could do that same procedure with R4 because we know the voltage and the resistance, so we could use Ohm's law to figure that out. But we can also use this other method. We know that we have 3 milliamps flowing in from the left. 1 milliamp of that current is flowing down, so the rest has to be flowing to the right. So how much does that leave over here? 2 milliamps, exactly. So that's the current for R4 is 2 milliamps. So that's how we analyze series parallel circuits. Again, it's not really any new techniques. It's just taking the techniques that we already know and applying them over and over again. So to find the equivalent resistance, we just look and try to find any resistors that are in series or in parallel, and then we simplify those using the formulas that you already know. And then you just repeat that process until you get down to a single resistor. Then you can find the total current for the circuit using the total voltage and the equivalent resistance. And then from there, you kind of have to work through it and try to see what information you have and what, where you can go with that, how you can build on that. So again, this is the shape of the circuit that you will be building on the midterm. So we've just gone through the process for analyzing this circuit. So that's the basic procedure that you will be using. Your numbers will be different than the numbers that I have up here, but the process should be the same. We still have a couple weeks before the midterm, but if anybody is curious, the midterm practice is available on Canvas. And again, it's just like this circuit. And you can take it as many times as you want, and the numbers change every time. So it's a great opportunity for you to practice that if you want to get started a little bit early. As we get closer to the midterm, we will work on this more, but that's just kind of the starting point, or an introduction to how we would analyze that circuit. So any questions about that? All right. So I know that was a lot of math. Thank you for sticking with me. But now we'll go on and we'll do a preview of today's lab. Yeah. Yeah.
Instead of going around this time.
Okay.
So I'm here. So
Yeah.
It doesn't mean that
Yeah,
I'll
yeah.
be back with the
For sure. All right. So the first part of, or the lab is starting on page 99 today. It's the series parallel resistor lab. It says series capacitors, but I think that's left over from the past. We're not actually going to be doing anything with capacitors today. So the first part of the lab is to open this circuit in Multisim. So is this circuit a series circuit, a parallel circuit, or series parallel? Yeah, series parallel, because R1 and R3 are in series, R2 and R4 are in series, and then branch A is in parallel with branch B. So this is a series parallel circuit. Some parts are in series, some parts are in parallel. So down here, so you would open this up in Multisim and you would make measurements. You would also do some calculations. So the first thing that you would do is you would calculate the resistance for branch A. So what would be the resistance for branch A? Yeah, 2 ohms, because you just have 2 1 ohm resistors in series. We just add those together. So branch A resistance would be 2 ohms. Same thing for branch B. That would be 2 ohms as well. So then you would have 2 branches that are in parallel, and each branch would be 2 ohms. So what would be the total resistance for that circuit? Almost. So you take the resistance of one branch and you divide it by the number of branches. So it'd just be 1 ohm, because you have 2 ohms divided by 2 branches. That just gives you 1 ohm. So you would measure this using Multisim, and hopefully your total resistance would come out to be 1 ohm. Okay? So then you would just repeat that procedure, but change the resistor values as is shown in the table here, and then you would take your measurements and write that down, fill out that table. So any questions about that part? All right. So then the next part, you would open this circuit in Multisim. Very similar, but now we have 3 branches instead of 2. Okay, so you do the same thing. You calculate the resistance for each branch, and then you use Multisim to measure the total resistance there. Now down here, this circuit is a little bit tricky. So the idea is that you're starting with this circuit over here on the left, and you want to find the equivalent resistance. So the way that you would find the equivalent resistance is that you would look for branch components that are in parallel or in series. So so when we look at this circuit, do you see any components that are in parallel or in series? Yeah, what do we see? Yeah, exactly. Exactly. So R1 and R3 are in series. So this branch is in series. Basically, each branch is in series. So if you were trying to find the total resistance, you would find the equivalent resistance of each branch and then redraw the circuit using those equivalent resistances. So that's what this problem is asking you to do. So it shows you this other circuit here that has basically done that. It's simplified each branch into just one resistance, but it wants you to, right now it just has a 1 ohm kind of placeholder value for each branch. It wants you to change the value of each branch to match the equivalent resistance that you calculated from the first circuit, okay? So for instance, for this branch, you have a 6 ohm resistor and a 2 ohm resistor in series. So what would be the total equivalent resistance for that branch? 8 ohms. So you would change this value here to 8 ohms, okay? So you go into the Multisim and make that change. You do the same thing for the other branches. Now, again, we're trying to find the total equivalent resistance for this whole circuit. So we have to look at our redrawn circuit and see if we see any resistors that are in series or parallel for this new one. So do you see anything in series or parallel? Yeah, they're all in parallel, right? The beginning of one resistor is connected to the beginning of all the rest. The ends are all connected together. So these are all in parallel. So you can redraw all of these 3 resistors as just one single equivalent resistance. So that's what we have over here. So they've been all redrawn with one resistance. Again, we have kind of a 1 ohm placeholder value, but you're supposed to change that value to whatever parallel resistance you calculated from the previous circuit. Now, if you've done your math correctly for all of these, their resistances should all be equivalent. And that means that the current flowing through each circuit should be the same. So these meters on the top of the circuits are all current meters. And if everything has gone right, the current through each of these meters should be the same. So that's what the question is asking. What is the total current for the circuit? So hopefully, when you change the values, the current should be the same in all of the meters, okay? So, and then down here it says print out the Multisim circuit. You can just cross that out. We don't need to print out this circuit, okay? So any questions about that procedure? Okay. So then you're going to do a very similar thing at the top of the next page, but with different values. Again, you're going to find the total current should be the same for each of these circuits. Again, you don't need to print out the Multisim circuit. So then the next part of the lab is to build, it says wire a circuit according to the schematic diagram. So you're going to build this circuit on a breadboard. So again, this is the circuit, the shape of the circuit that you will be building for the midterm. So definitely take some time and make sure you can put that together. Here is an example of how I put that circuit together. Remember, when I build circuits, I like the circuit on the breadboard to look similar to the circuit in the book. It helps me keep things straight in my head that way, and it helps me not get confused. So I built this circuit on the breadboard to look kind of the way that the circuit does in the book. So the book has a power supply on the left. I've got these two wires on the left side that would go to the positive and negative leads from my power supply. Then there's a R1 is on the top, so I've done that there. R4 is on the bottom here. And then R2 and R3 are kind of in the middle and the right side of the circuit respectively. So that's what I have put together here. So there are millions of ways of creating this circuit on a breadboard. This is just one, but I like to do it this way because it kind of keeps things straight in my head that way. Okay. So for this part of the lab, you will build a circuit on the breadboard that matches this schematic, and then you will find the voltage across each of the resistors and the current through each of the resistors. Okay? So, any questions about that? Yeah.
For part A on the right, where it says total R, or do you want us to put the, oh, never mind.
So,
No, I figured you did.
yeah. All right, so then the last part of the lab is to build a circuit on a lamp board. So the lamp board is this board that looks like this. It's got 3 lamps on this board, and each lamp has one terminal that's connected to the top screw and then the other terminal that's connected to the bottom screw. Okay, so your diagram in your book has 4 lamps, but we only have 3 on this board, so you can just cross out this bottom lamp. Okay, so instead of having a lamp there, that's just going to be a straight wire. So, and then you can just cross out the voltages for lamp 4 and the current for lamp 4. So what we're going to do is we're going to use these alligator clips to make the connections that are shown here in the book. Okay, so this circuit might look kind of straightforward, but it's often confusing for students. So let me just take a minute to go through it. So basically, the way that I look at this is I just do kind of like connect the dots. You know, I look at one point, see where that's connected, and make that connection one piece at a time. So, so I have the power supply. This shows the power supply connected to one side of L1. So I'm going to take my red lead from my power supply, connect that to one side of L1. Now the other side of L1 is connected to the top of L2. So I'm going to take one of these little alligator clips. I'm going to clip one end to L1 and the other end to L2. So now I've made this connection from L1 to L2. Now the top of L1 is connected to the top of, the top of L2 is connected to the top of L3. So I'll use another alligator clip to do that. The bottom of L2 is connected to the bottom of L3. So I'll do that. And then finally, the other side of the power supply is connected to the bottom of L2. So I'm going to take the other lead from my power supply, connect that to the bottom of L2. Okay? So that's how we set up this board. Kind of the trickiest part is that L1 is shown going horizontally in the book, but it's actually vertical on the board. So you just kind of have to imagine tilting this lamp around, and then everything kind of makes sense, I think. Now, if we look at this circuit, the power supply is going to be connected directly to L1. So is L1 going to get all of the current that flows out of the power supply, or is it going to get only part of it? All of it, because that's the only place the current can go. So all of the current has to go through L1. But now, after it comes out of L1, it reaches this junction, and some of it goes to L2, and some other part of it goes to L3. So is L2 going to get all of the current from the power supply? No, and neither is L3. Now, remember, the brighter, or the more current you have, the brighter the lamp glows. So are all of these lights going to be glowing equally as bright as each other? No. If this is wired up correctly, L1 should be much brighter, and L2 and L3 should be very dim, almost to the point where you might have a hard time seeing that they're lit up at all. Okay, so that's kind of a check to make sure that everything is working right. So that's the lab that we're going to be doing for today. So any questions about that? All right, then let me take attendance, and I'll let you go.